All right, so I'm going to be doing Add Math Paper 2 from February, March 2022. And let's jump into number 1. Number 1, we're given a line L, 4x plus 5y equals 9. Notice that it's not in standard form. Have 2 points, A and B, and we want to find the equation of a line parallel to L that goes through the midpoint of A and B. All right, let's talk a little bit first just generally about lines. Basically, there are 2 things I need to know to fix a line. When I say fix a line, I mean it's a specific, unique line, and we can give the equation in that case. All right. I'll do a little illustration here. What if we know? So we need 2 things, I should say. What are they? We need the gradient, and we need a point, any point, and that will fix the line. What if we have only 1 point? Then this rotating line shows all the different directions. So we don't know the direction, we know a point, and there are an infinite number of lines that can be drawn in that case. Okay? We don't know the direction. So those are all the different possible directions. All right. What if we know the direction, but it's not fixed at a point? So these lines here are all parallel, but again, there's an infinite number here because it's not fixed at any point. All right. So to be able to write the equation of a line, we need 2 things. Okay. So here are the things that we are given in our problem. The blue line is L. We have our 2 points, A and B. And so we're told that the line that we want is parallel to L and passes through the midpoint of A and B, which is the pink point there. All right. So the 2 things we need, gradient and the point. The point will be the midpoint. Let's find the gradient. So we take our line, we want to put it in standard form now. Okay, so just a little bit of algebra here. Get the y isolated. Okay, and that's good enough. We'll just clean it up a little bit. Okay, so that shows our gradient and our y-intercept. Gradient is -4/5. Okay, there's one piece. Now we need a point. So we know the direction, we need a point. The point that we're going to find will be the midpoint because that's what we're told. We're told it goes through the midpoint. Okay, so we need to find the midpoint here, which is basically just the 2 x's divided by 2, and then the 2 y's divided by 2. That gives us the midpoint. And we will simplify this a bit. -5/2, 16/2, and then a little bit more simplification. There we go. Okay, so we've got a point, we've got a gradient. That's all we need. Now we just need to know this little formula. Okay, this is what you can use when you have a point and the gradient. So our y value is 8, our gradient is there, our x value is -5/2. You could probably stop here, but let's clean it up a little bit, get those 2 negatives, yeah. Okay, but you don't have to put it in standard form. That is the equation of the line, so that's good enough. You'll get your marks for that. All right, so that was a pretty nice way to get started. The formula for a line where you have a point and a gradient, really a key formula. You'll use it a lot. And if you think about it, it makes sense, right? If you have the direction and you have a fixed point, that's a unique line, and so we can get the equation. All right, that's number 1. We should be off to a good start. 3 marks there. And let's go and look at number 2. All righty, on to number 2. We have a log equation. It says solve the equation. That means find x. Okay. And I highly recommend you try to work these out as much as you can, as far as you can, without help. Then that will really show you your strengths and weaknesses. Then the illustrations would be useful, hopefully, to uncover some things that are in darkness, I guess. All right. So with logarithms, there's this relationship changing from a log equation to an exponential equation. Okay. This is really, I think, the key to being able to work with logarithms. Understanding how to go from log expressions to exponential expressions, or vice versa. I'm going to run this one more time. So we start with the log, base a of x equals b. So a is the base, b is the exponent, and the answer is x. Okay. This is the key to logarithms. Okay, so that's up there in the corner, and we'll see how we use it. Here's our equation, and we're going to first use one of the log rules. When we subtract logs, we can also write it as a division. Okay, so you need to know your log rules as well. They all come from, you can derive these from the basic information in the corner. And that's really useful. I'm not going to do it here, but I really recommend that. Just will solidify your understanding. Okay, so we rewrite the left side as a fraction, and then we're going to use the relationship that I showed. So the base is 5, the power is 2, and the answer is there, the fraction. And now, pretty easy to solve this. Rearrange it a bit. We've got just a linear equation. We have 50x, and we subtract 8x equals 7. And from there, no worries. Divide by 42. Simplify it. That's it. Okay, so that is a pretty quick 3 marks. And the key there is to being able to work with logarithms. It takes a little bit of practice and a little bit of time to get your head around what these things mean. But if you can look at that relationship in the corner and really just try to tie everything back to that as much as you can, I think you'll see that these are easy problems. So a nice 3 marks there. All right, we're off to the races, I think, with these first 2. And we'll expect it to get a little more challenging, probably. So let's see what we have. Okay, question 3 is a probability question. We have a group of students, 4 girls and 3 boys. Stand in a line. Okay. A. Find the number of different ways the students can stand in line if there are no restrictions. Okay. So one thing that we need to point out here is that the students are all different, right? They're not clones. Like the 4 girls are not clones. The 3 boys are not clones. So it does matter what order they're in, right? When we say different ways, that means different orders of these individuals. Okay, so order matters. Part B. Now there's a restriction, and the restriction is that the three boys need to be next to each other. Okay, they can't be apart, so they need to be next to each other. And part C, we identify two girls with names, and there's a condition that Cam and D are not next to each other. Okay, so we'll have to think about the scenarios that satisfy that. Okay, so let's look at number one. Here are my people. So they're all individuals. The girls are identified by skirts. In math, we try to avoid controversy. So we just want to be clear. That's all. So try to bear with me here. Girls are all wearing skirts. Boys are not wearing skirts. Okay. So how are the different ways that we could arrange this? Well, let's think of the first slot, right? We have 7 individuals. There are seven different ways to choose that. Okay. Now with the second slot, there are only 6 remaining because the one's gone, right? So there's 6 ways to choose that one, and so on. There's a basic permutation of 7 items, and there are 7 factorial ways to arrange that. Okay, that's part A. That's fine. Let's look at part B now. The 3 boys need to be together. Okay, so let's take the 3 boys and we'll put them in the different positions where they could be. So they could be in the first 3, right? They could be from 2 through 4, 2, 3, 4. Okay. And we're just counting them here, right? So there's the 3rd way. There's the 4th way, and you get the idea. The 5th way. So there are 5 basic positions where the 3 boys could be. Okay. Now we care about the order of the boys. Okay. So let's think about them in the first position. So 1, 2, and 3. And how can we arrange these 3 guys? Well, it's similar to part A, right? We have 3 factorial ways to arrange 3 individuals. So we have to multiply that by the 5 ways. And then for the remaining girls, this is also similar to part A with 4 individuals. We have 4 factorial. And so there you have all the ways for the 3 boys to be together. Okay. Finally, we have 2 girls that are named Cam and D. They cannot be next to each other. Okay, so there's 2 different scenarios where this could happen. The first is where Cam is on one of the ends. So Cam is in the first slot, or she's in the second slot. Not the second slot, the last slot, yeah. Okay, so those are 2 ways. So we have 2 there, and try to see why those are identical. Those are going to be identical, right? Whether she's in the first or the last, how the rest of it sorts out is going to be identical. So I can just do 1 and then multiply that by 2. Okay, so we'll put the 2 over there, and we'll put Cam in the first slot, knowing that if she was in the last one, we could repeat the exact same thing. Okay, so what are the restrictions on D? Well, she can't be in the second slot. All right, where could she be? She could be in the 3rd. We have to count all these up now. There, so we're just counting how many available slots are there for D, and you can see that we're going to get 5. Okay, so we multiply that. Okay. I'm going to leave her in the last one, and we again recognize that any one of these 5 slots where D is, we're going to have identical calculations going forward, right? So we don't have to do it 5 times. That's why we multiply by 5. We do it one time because they're all the same, then we multiply by 5. Okay, the 5 remaining individuals, just like part A. Okay, because the order matters, there are 5 factorial ways to arrange them. Okay, so that's the first scenario. Let's go back to the start now, and this is where Cam is not on the ends. She's somewhere in the middle. So I count all those up. You can probably do this in your head much quicker, I would think, but I like my little colorful people, so. 5 ways, right? 5 places for Cam to be. All right. Let's put her in the second one, recognizing again that doesn't matter which one we look at. The 5 different calculations here are going to be identical. So we just do it one time and we multiply by 5. Where could D be? Let's look at where D can't be first. She can't be there. She can't be there. How many remaining places? Just count them up now. 1. Oh, it feels slow now. 2. 3. 4. Okay. So there's always going to be 4 places where she could be. So we multiply by 4. And then we have our remaining 5. Very familiar now. 5 factorial. Okay, so we have these 2 scenarios, and to get the total, we just add them up. Okay, so there you go. There you have it. I'm going to leave the calculator work to you. You might see that that's actually 30 times 5 factorial, if you want to simplify a little bit. All right. Yeah, counting problems. Fun. But can be confusing. Got to really think about, like, does the order matter? Questions like that. But like everything, practice makes it easier. Okay, that's all for number 3. Okay, to number 4. Number 4 is simultaneous equations, actually, but not in the linear form that you first learn. So how are we going to solve this? We wouldn't want to use elimination because we've got like x squared, y squared in the first equation. Then we've got basically a reciprocal type function in the second. So there's no clear, easy way to use elimination. But substitution is pretty clear because we know we have an expression for y, right? We're given that y is 3 over 2x. So we'll just use that to substitute. I'm going to talk a little bit about picturing things. Obviously, on an exam, you're not going to take the time to draw these things out. But it's good, especially when you're doing practice, to try to picture what these graphs might look like. And I would recommend using Desmos. You can just put these into Desmos and then you just see exactly what's going on. Really nice. I'm using, for my illustrations here, I'm using something called Manum, which is it's a library in Python. And if you're keen on Python, or you just you interested in learning some Python, this is a super fun tool. I've just been having a blast with it. So if you're curious or interested in that, you can leave a message in the comments. I could help maybe point you in the right direction. Yeah, programming is quite a lot of fun, actually. Okay, so I'm going to show you what these look like. Again, I know you don't have access to this on the exam, but what the heck, it's fun. Okay, so I should say, yeah, the first equation, the x squared over 4 plus y squared over 9 equals 1. That's an ellipse, okay? So you may or may not know that. The second one is, as I said, a reciprocal function. And so we look at this and we say, okay, how many solutions could we have here? It's a good thing to think about. If we have two linear equations, then we know there's only at most one possible solution where they intersect because they're straight lines. There might be no solutions if they're parallel. Okay. For this case, we could have up to 4 solutions. But when we see that ellipse shrinking, we might have 2 solutions. We might have no solutions. Okay. So if you have a little picture of what's happening, that can prepare you to look at your answers and determine if they're reasonable, basically. All right, but anyway, there's no avoiding it. We got to go through all the algebra, and so there's going to be a boatload of equations here, and try to do it on your own, obviously. But it's really just an algebra problem. Being able to manipulate the algebra. This is a big thing of AdMath, and it's a great preparation for further math because you really want to be good at algebra. So, yeah, this is just a big algebra question. Okay, so we know what y is, and we're going to just stick that in for y squared. And we're just going to we're going to simplify that numerator there. So we get 9. Yeah, we just squared everything, right? 9 over 4x squared. Now the next move, you notice there's we got two fractions on the left side. In the second fraction, we've got a 9 in the numerator and a 9 in the denominator. So those cancel. Now, if you're not sure about the truth of that, or you're not sure why that is, then here's the time to pause and just work it out in a way that makes sense to you and to just verify that the 9s cancel. The 4x squared ends up in the denominator. All right, we need to simplify this. I want to get rid of the fractions if I can. So I notice that if I multiply by 4x squared, all those denominators will cancel. Okay, so the first one, we end up with x to the power 4. That one, everything cancels. We just have 1. And on the right side now, we have 4x squared. All right. Now we have, it's called a quartic. But we haven't learned specifically how to solve quartics. But you should hopefully notice here that you can think of this as a quadratic. And so instead of x, we have x squared. And instead of x squared, we have x to the power 4. So you think of your variable, instead of x, your variable now is x squared. Okay, then we can think of it as a quadratic. We solve quadratics by putting everything on one side. We subtract the 4x squared. Okay, so we basically we can use the quadratic. Okay, first of all, I should say you can try to factorize this, but you'll see that you can't, right? Because you need to make 1 with the multiplication, and then you need to come up with -4, and it's not going to happen. So we got to use the quadratic equation. So the quadratic equation, now we're solving for x squared, not x. But everything else is the same. So x squared equals -b plus or minus square root b squared minus 4ac all over 2a. All right. And then we just go through the calculations here. So as you notice, okay, so I should say inside the radical, you get 16 minus 4. Got 12. Let's simplify that square root of 12. Yeah, and then so we have common factors there of 2, so we can divide out of 2, and we are left with 2 plus or minus square root of 3. Okay. So treating it as a quadratic, we get 2 answers. Okay. We're not done yet now because we're not looking for x squared, we're looking for x. Okay. That's no problem. We're going to have to take the square root. Okay, so first let's just notice that for x squared there's 2 answers. So I'm going to do one at a time. I'm doing the plus first, so I'm doing 2 plus square root of 3, right? I'm taking the square root of that, and I have 2 answers for that. So we basically have 2 answers times 2 answers, which is going to be 4 answers. And that was what I indicated with the ellipse, okay, touching the reciprocal functions 4 times. All right. So I'm looking at 2 plus square root of 3, and then for that I get 2 answers, plus or minus. Then you can just put it in your calculator. So we get plus or minus 1.932. Then we have to look at the other case where it was 2 minus square root of 3, and for that we have 2 answers, plus or minus. And that's also just a calculator at the end. All right, so 4 answers. They're only asking for the x, so you don't have to get the y. 4 answers, and there you have it. All right, done, number 4. Okay, number 5. We have a and b, they're totally unrelated. So a, we're told that this is a modulus function or absolute value of f of x, and f of x is a quadratic function. All right, so you notice there we have the roots, right, at 1 and 4. We have the y-intercept at 4. Okay. And then b is cubic and completely unrelated to a, so yeah, we'll have to go through that. All right, so let's look at a first. So here's our function, and we want to know what are the possible f of x's where this came from. All right, so I don't know anything better than to say, like, hopefully you've seen this and it's familiar, and you would know that because it's absolute value, that that means it can't go below the x-axis, right? So I think of it as the function like bouncing when it hits the x-axis if it's starting from the positive. So, but there's 2 possibilities here, and this is not the most rigorous way to do it, but I'm just gonna say that it's relatively obvious, isn't it? I don't know. I mean, I'm going to draw them out. So we could have this case where the x squared is positive, right? And so the blue stuff below the x-axis basically is reflected back up to there, and so that it would make our function. Okay. So that's what I'm going to call the positive case. All right. But we also have this negative case. If we started negative, so this is like a negative x squared. Okay. So the two branches, let's say branches below the x-axis, those would both get reflected back up above the x-axis, and they would also make our function. So it would look like that. Okay, so those are the two possibilities. And now, since we have the roots, we have the y-intercept, we can do this. All right. So let's look at the positive case. Okay, so we have the roots, 1 and 4. There might be a number there, a, that this is multiplied by, that we have to check for. Okay? So I'm just showing here where the 1 comes from and the 4. Those are the roots. Okay. All right. And then we know that f of 0 is equal to what? So f of 0, that's when x is 0. The value of the function is 4. All right. So this can give us our a. And conveniently, so this is like, if you forgot that you needed to find a, you're probably okay because it's 1. And so people who didn't bother with finding a can still get this correct. But it's possible that a is not 1, so you really should check that. Okay. So there's one function. Okay. And then the other one is just, I guess you just say it's multiplied by -1. I mean, it's fairly obvious, right? When you multiply by -1, it just flips everything down. Yeah. So you got all the same roots, right? You could check the y-intercept is going to be -4, right? Okay. That's it, though, for a. Actually, not a big problem. Okay. Now to b. B is a cubic. So I'm drawing this is not specifically our cubic, maybe it is, maybe not. Typically, a cubic could have 3 roots. Okay. And in this is a case, they told us that there's 3 roots. So it's basically going to look something like that. If the coefficient in front of the x cubed is positive, it's going to start, what do I say? It's going to start below the x-axis, and then it's going to end up above it. So that's our basic shape. Okay. So here are the roots. We're given one of them specifically, and the others are in terms of n. We're also told that n is less than 0. Okay, so that's important. Okay, so I'm just going to make a cubic with the roots, right? So we just take x minus the roots, and it's 3 factors, right? 3 factors because it's a cubic. Okay. Now, we also have 5x cubed, right? So we know we have 5. We have to multiply by 5 somewhere. So let's just put that in front. And then to simplify a little bit, I'm going to multiply 5 into the first factor so I can get rid of that 1/5. Okay. And so now this is fairly neat form of our cubic. Okay, so what can we do here? basically what we can say is that the constant value of -2 can be made by multiplying the negative root. Yeah. So the second term in each factor. When I multiply those, that is the only way. That's the only thing that makes up the constant of -2. So I'm going to just do that, multiplying all these things together. Make sure you put the negative n and -1 in brackets, right? Because it's like one thing. Okay, that equals -2. I'm just going to multiply out the left side now. So we got that. Okay, just go through it yourself, make sure, double check, maybe I have a mistake. Okay, we got all these negative signs, so we'll do this next. We add 2 to each side. Okay, good. And then I want to change the signs here. I'd rather have a positive n squared so I can multiply everything by -1 just to switch all the signs. There's 0 on the right, so 0 is not going to change. Okay, this is a nice little quadratic. We can solve it by factorizing. And we see that n is -2 or 1. Now go and look at our orange box there in the upper left and remember that n is less than 0. So we can throw out the 1. So n is -2. Okay. So we'll put that in for n now. Okay. That's our polynomial, p of x. So we put in the -2. That gives us, for the second factor, x plus 2, and for the third factor, x plus 1. And then let's just expand all these brackets. Okay, now this is a skill that is really, really important in ad math. It just comes up all the time. So you want to do tons and tons of practice of expanding brackets. So much so that it becomes, like the times, no, not the times tables, but I mean, it's just like, it becomes so familiar that you think of it as something that's easy. That's the best way I can say. Okay, so here we're going to just do one at a time. I'm just going to multiply the first factor times the second. Okay. We got 4 terms. We'll combine the like terms. And so now we'll have a quadratic as one factor times x plus 1. Going to expand those now. So it's a 3 by 2. We should end up with 6 terms, right? Let me just explain what I did there on the last one. We're multiplying. So the second factor is x plus 1. Okay. So the 1 means I don't really have to do any work here, because if I multiply the first factor by 1, I just write down the first factor. I just repeat it. So I didn't have to think much there. Okay, so anyway, there's my 6 terms. We want to combine like terms. And then just be careful. There's all sorts of places to make silly mistakes here. But then you're done. That's the A value. There's the B value. All right. So, yeah, as far as cubic questions, that one wasn't too bad. We didn't have to do any long division, so that was good, I guess. Yeah, just a lot of algebra and plenty of places where you can make a silly mistake. So just be careful. You need to just practice a lot of this stuff, especially expanding brackets. Just do tons and tons and tons of them so that you're familiar. And if you do a lot of practice, if you do make a mistake, which always happens, not always, but for me always, but often happens, you'll catch them quicker, right? Just from your experience. Little things with the positives and negatives. Okay. Done with number, what was that? 5. Yeah. Okay. Onward. Okay. So we're looking at some questions using the binomial expansion. First one is 1 plus 3x to the power 7. Now, I was talking earlier about how you need to be good with expanding brackets, right? And you could expand the brackets like power 7, but man, you really don't want to do that. It would take a long time, and the chance that you would have no mistake is so small that doesn't make sense. Luckily, we have the binomial expansion. It's given to you in your formulas. So we're going to use that. Typically, the binomial expansion really simplifies things. But it is also tedious if you were going to totally expand this power 7, you'd have 8 terms. So you don't really want to do that either. Usually, you are only looking for specific terms or up to a certain amount. So the first one, part A, we're only going to go up to x power 3. So that's not so bad. We don't have to do the whole thing. Next one, we have 1.03 to the power 7. And if you've seen this before, you will notice the relationship of A to B. And so that's really important here. So if inside the bracket you have 1.03, and you could think of that as 1 plus 3 over 100, and now it really looks very similar to A. So you want to try to think of how you can make that look similar to A. And they give you a clue there because they say use A to solve B. All right. And then the C part, we've got power 15. Now talk about tedious. If you wanted to expand that all the way out, you'd have 16 terms. And now you really want to think about a way to get a shortcut there. Okay. So here is our binomial expansion. I'll stash that away in the corner so that's in the back of our mind. We're going to expand the 1 plus 3x to the power 7 until we get x to the power 3. So I put that approximate sign because this is not obviously the exact answer. It's really only part of the answer. Okay, so how far do we need to go? We just need to go up to there. All right, so I have a few things to notice here. Notice that the blue power plus the red power always equals 7. Okay, it's a thing to check. You notice that if we're you can go in either, or you could switch the 1 and the 3x, right? You could say 3x plus 1 and switch the order, and it's the same thing. So you can choose which way to do that, whichever suits your problem better. In this case, we want to do ascending orders of x, right? So we start with the 3x to the power 0. Okay. And then, so you see in that case, the red, we have as part of the coefficient 7, choose 0. The 0 is red, and so the reds are the same. Something to notice. Okay, now in this case, we have all these 1s, and we don't care what power they are. They're just 1, so they basically just vanish. And so we can simplify this. We take the first term, 7 choose 0 is 1, and that 3 to the x, yeah, it's going a little fast. Okay, so you should pause it and make sure you match that. Okay, but you can get those combination functions like 7 choose 2, 7 choose 3. You can get those on your calculator. And just going to simplify it there, and that's it. So part A. Okay. And then so B is related. And what you want to notice here is how can you write this in a binomial way. Okay. So we break it into two pieces. We have a 1 and we have the 0.03. And I wrote it like that. So this really indicates the relationship to part A. So that we have the 0.01 is kind of now in place of the x. And that means we can just throw it into our result from A. We put 0.01 in for x. And then it's just a calculation. So not a tough one, but you got to recognize the relationship of part A to part B. And you got to think about how you can make part B look like part A so that you can identify, what is the x? In this case, the x is 0.01. All right. And then you don't really need a calculator here, but yeah, probably going to use it. Then we can give it in three places. All right. That's part B. We have this binomial expression to the power 15, and we need to know, let's see. Okay, we need to know the term independent of x, right? Okay, so that would be one where the x's cancel. Okay, so I wrote a program, pretty nice. It just runs through these. Okay, so I don't have to do any work. I just plug in the two terms of the binomial, the n value. It's going to run through them all. You don't want to do this though. I'm showing it just so you can see what's happening. But the first term there, our goal is for the x's in the numerator to cancel the x's in the denominator. Okay, so we want the power of x in the numerator to equal the power of x in the denominator. Okay, the first term is obviously in the numerator we're going to have x to the power 60 and x to the power 0 in the denominator. So that's not even close. So what you want to do is try to jump ahead and see what's going to happen. But this illustration might help you to see that. But I don't want you to write all these things out. Just look at them and notice the pattern, what's happening. Okay, so as we proceed here, the power in the numerator is getting lower, the power in the denominator is getting bigger. When are they going to be the same? Okay, keeping in mind that the blue plus the red must equal 15. Okay, so try to think about when we're going to hit this. When is the power in the numerator and the same as the power in the denominator? Okay, so they're approaching each other, but they're pretty far apart. All right. But the numerator power is going down, the denominator is going up, and try to think when are they going to be the same, given that the blue plus the red equals 15. So hopefully you're you've got an idea here. Okay. If you program it, it's no extra work. It's a nice thing about programming. Okay. Maybe I'll pause it here and just see where we are. Okay. So in the numerator, we've got x power 24. We've got in the denominator x power 9. Still not that close. Getting closer. When do we hit it? Let's see. $16 in the numerator, 11 in the denominator. And now we have it. Okay, nice. So we have 12, x to the power 12 in the numerator, and we have x to the power 12 in the denominator. They're going to cancel, so they're independent of x. This is what we want. And that, in green, we just have to calculate. Okay. Now my program is going to go all the way to the end. But we're almost there, so that's fine. Just notice the patterns here. All right, that's the last one. 16 total terms. It's 15 plus 1 total terms. You don't want to do that by hand. You really don't. Okay, so here's our answer, and we just have to do the calculation. The x's are gone. The 2's simplify. You put the other stuff in your calculator, and you're done. Right. All for number 6. Okay, on to number 7. Here's a trigonometry question. So first, let's notice that all angles are in radians. Okay? You really want to be able to switch back and forth between degrees and radians. You shouldn't be scared of radians. You just got to have some experience with them. So it's not a problem. Make sure your calculator is switched to radians. So you can do that now. So A is an equation we solve for theta. Okay, one thing to notice here is the range. Typically, we see the range is from 0 to 2 pi, right? And 2 pi is a full circle. Here, we're starting at negative pi. We are traveling a full circle because traveling around back to pi, okay? But it's at it's a different starting point than normally, I would say. Okay, but we'll look at that a little closer as we get into it. Part B, we have an angle phi, another Greek letter. Common again, like after theta, it's the most common Greek letter for an angle. And what are we going to do here? We're going to just show this identity. Notice that phi is from 0 to pi over 2. That means first quadrant. Okay. You want to know where you are, like as far as which quadrant you're in, based on these ranges. Okay. And C is, we're given a cosecant value, and we're going to have to find the cotangent. All right, and again, look at the range. 3 pi over 2 to 2 pi, that's the fourth quadrant. All right, let's get into A then. So A is secant squared theta equals tangent theta plus 3. Now, I would like to have all same trig functions. Okay. And so luckily we have an identity for secant squared. It's on your formula page. And secant squared is equal to tangent squared plus 1. Okay, now we have all tangents. That's nice. And we have a quadratic equation. And you might say, what? It doesn't look like a quadratic equation. And so what you want to do is think of tangent theta as an unknown. It's a thing that's unknown, like x is a thing that's unknown. And so we have this thing, tangent theta, to the power 2. So that means it's a quadratic. And so we're going to solve it just like we would any other quadratic by bringing things all to one side. So we subtract tangent theta, subtract 3. So it's all equal to 0. And then we want to try to factorize it. And it is easily factorized, like so. That means we have these two answers. Tangent theta is equal to -1 and or -2. All right. So let's put that up in the corner there. And so now, based on that, we need to find theta. Okay. So now it's really critical here that you draw unit circles and you think about what quadrant we're in. And for this problem, we have to also think about the range. It's from negative pi to pi. Okay. So anyway, let's start with the 2. So first you're going to use your calculator and you're just going to get the inverse tangent of 2, and that's going to give you your first value for theta. Okay, no problem. Let's see what it looks like on the unit circle. So remember, we're starting at negative pi. So that's indicated by the yellow arrow. Okay, you can think of, if we start at 0 and you go clockwise, which is negative, you land there after negative pi. Okay. Okay. Now we're gonna what I want to show you is getting to the theta value from your calculator. You see it's 1.11 radians. Okay, so we're going to start at negative pi. We're going to go in a counterclockwise direction to our answer. Boom. Okay. And this is also the reference angle. Okay, so that's our first answer for theta. It just comes from the calculator and looks like that. All right, now the second answer is, again, we're starting at, okay, let's first think tangent's positive, right? So it's first and third quadrant. We got the first quadrant, now we got to get the third quadrant. Okay, and don't forget we're starting at negative pi. So basically, if I start at negative pi and I add the reference angle, okay, so it looks like that. Negative pi plus the reference angle is going to give me my next answer. Let's see what it looks like on the unit circle. So I start at negative pi. We travel in a counterclockwise direction. We go 1.11 radians from negative pi, and it gives us negative 2.03. All right. Now we have to do -1. Again, we'll put that in the calculator, inverse tangent, -1. And I think most calculators here will give you the answer in the fourth quadrant. So again, you have to remember here that there's more than one answer. So when the tangent's negative, we have answers in the second and fourth quadrant. Okay, so yeah, pretty sure all calculators will give you the fourth quadrant answer. So it's going to be a negative. Let's see what it looks like. We travel from negative pi to there. All right, it's negative 0.785 radians. And to get the final answer now, okay, would be the second quadrant. So we're going to travel from negative pi in a counterclockwise direction, and we're going to be 0.785 short of pi, and this is what it looks like. Traveling in a counterclockwise direction, and we stop here, 785 short of pi, and that's where we get that fourth answer. All right, that's part A. Part B now is an identity, and how do we approach these things? I guess this one, you need to just recognize when you see 1 minus cosine squared, that's supposed to light something up in your head. And you need to recognize that that can be written as sine squared. It comes from the sine squared plus cosine squared equals 1. So the first step is to rewrite that. And then the second step would be to change the secant to 1 over cosine. I guess I should say, why am I doing this? Typically, my goal here is to get into sines and cosines. I'm a bit more familiar with them. I feel like they're easier to work with. So if I have these opportunities, like to change the secant, I'm going to usually do that. All right. And then we're going to have the square root of sine squared, so that's nice. And it's looking already pretty good, I think. Remember, we want to show that the left-hand side is equal to the right-hand side. What I'll do here is multiply each side by sine. And then, pretty obvious, that we have tangent theta, tangent phi on both sides. So that's done. Yeah, it was in the first quadrant, I guess. That means, yeah, I should have backed up a little bit. When we had the square root, we can throw out the negative answer and have only the positive answer. So that's why it's important to know that we're in the first quadrant. Okay, but I think that work is enough for all the marks. Okay, the last one, C. Start with cosecant. Like I said, usually I like to just change into sines and cosines if I can. All right, so we got the sine, and then I'm going to just flip that, the reciprocal. All right, now I have something that I can think about. I can make a triangle, right? Remember that the range told me that we're in the fourth quadrant. So that makes sense. The sign is negative there. And it means that we can ignore the third quadrant answer. So we only have to look at the fourth quadrant. Okay, here's where I want to draw a triangle. We can get everything we need. Everything about a triangle can be found out if you have just one trig ratio. All right, so here's the triangle. You see the opposite over the hypotenuse is negative 8 over 17. We have that unknown side. I'll call it A, but we can find that with Pythagoras. All right, so let's do the work over here. Okay, so I'm showing here the sine, yeah. So that's the triangle we're looking at. And then I want to find A, so I'm going to do the Pythagoras. Okay. It's good to know your square numbers. On the left side, I subtracted the 64, and so that's A squared. And then it gives me 225 on the left, and hopefully you know that that's 15 squared. So A is 15. Good. Now we know everything about the triangle, and you can get any trig ratio that you want. I think we're looking for the cotangent, right? Cotangent is the reciprocal of the tangent. So it's the adjacent over the opposite. Adjacent over the opposite. There you go. That's it. That's all you got to do. Got to draw that triangle. That's the key. Yep. Okay. Okay, number 8. We're going to deal with sectors and arc lengths. And there's a couple nice little formulas for calculating those, which you should have memorized. And even if you didn't even if you don't have it memorized, it's not like it's definitely doable. A sector is just a portion of a circle, right? And an arc length is just a portion of the circumference. Okay, so yeah, I guess let's look a little closer here. So we've got this sector split into two pieces. One is a triangle, and the other one is a whatever leftover shape, doesn't have a name. Well, we're told that the exact value of A is such that the area of the triangle AOC is equal to the area of the shaded region. Okay, so you split it into these two pieces which are equal. And then we could also say that the triangle then is half of the sector. So that's basically what we're going to be using. All right, and then for B, we use the answer in A to find the perimeter of the shaded region. So that's just it's two line segments in the arc added together. Okay, so let's start with A. Okay, so here's our diagram, and I'm going to take the triangle, I'm going to pull it out. This is useful for me sometimes to help me just separate things, because there's a lot that the triangle can give me. And if I look at it as a separate thing, sometimes easier. So I'm going to pull it out, I'm going to rotate it. Okay. And I'm interested in the height of this triangle, because if I can get the height of the triangle, I can get the area, because I know the base. Actually, the base is 15. All right. So that's my main puzzle right now. So let's see how we proceed. Okay. So as I said now, the area of the sector. So half of the sector is equal to the triangle. Okay, and that was given basically. All right. So let's write down the area of the sector. Now I'm bad at memorizing formulas. So what I do is I just say, okay, take the angle, pi over 6, divide that by 2 pi, because that's the full circle. That gives me the proportion, right? And then I multiply that by the area, which is pi r squared. Now there's a better way. There's a better formula if you memorize it. And it's just, well, you see the pi's cancel there. So you basically have 1/2 times the angle times the radius squared. That's the formula. So you should memorize that. Okay, so we do a bunch of simplifying here, and we end up with that. And that is the area of the sector. Okay, so that's a known number because we know pi. And then the triangle is going to be, okay, first let's write the triangle in terms of h. Okay, so there is the triangle, 15h over 2, base times height over 2. And we know that that's equal to half of the sector. So we can equalize these two things and solve for h. Okay, after some, you see the 2's in the denominator cancel. We'll bring the 15 over, and we're just simplifying here. We got 225 in the numerator and 15 in the denominator. That can simplify. And we can go a little further, divide by 3, 5 over 4. So that's the height. Okay. Now what? We want to find a, small a. And so what we can do, since we know the height of the triangle, okay, we can look at another triangle, a right triangle there, with this angle pi over 6. So if I take the sine of pi over 6, that's h, over the hypotenuse in that small triangle is OC. All right. I know h, which means I can find OC. Okay, so we just rearrange that. By the way, sine of pi over 6, anybody know that offhand? It's the famous 30, 60, 90 triangle. So it's good to know these things. But you also have a calculator. But it is a half. All right, that means we know OC in terms of h, and then we know h, so we know OC. So we put in h, and finally, OC is 5 over 2 pi. Okay, so there it is. That means we can find a, because OC plus a is the radius, so it's 15. And so a is just 15 minus OC. All right, that's part A. Let's stash that away, something we found. All right, now we need the perimeter of that red section that's made up of 3 pieces. We found one of them just now. Okay. So let's just make sure we can see all these pieces. CB, okay, that's also known as small a. So we have that. We have to get the arc length of AB, and then we have to get AC. So those are the 2 outstanding bits. All right, let's get the arc first. Okay, so I told you I'm bad at memorizing formulas. So what I take is the angle that forms the arc, pi over 6, divide by a full circle. That gives me the proportion of a circle. And then I multiply by the circumference, which is 2 pi r. Now you can see, obviously here, the 2 pi's cancel, and I didn't have to do that if I just memorized the formula. So guys, memorize the formulas. It's just pi over 6 times 15. It's just the angle times the radius, right? That's it. Okay. So there you have it. There's AB. Should we simplify it here? Yeah, let's divide by 3. Okay, I got 2 pieces. Now I need AC. Okay, it's not as easy as you might hope. You're going to have to use the cosine rule here. That's okay, though. No problem. It's given to you, right? Yeah. Okay, so just got to put all the pieces in the right place. So we're looking at that triangle that we first pulled out, and we have, let's see, we have the opposite angle. That's why we're using the cosine rule. We have the 2 sides. So we have everything. It's just set up very nicely for the cosine rule. So just put all the pieces in the right place, and it's just a big thing you put in your calculator, right? So just put the square root sign in your calculator, put all that stuff in, make sure you got brackets and all that stuff. You got to be really careful with your brackets and make sure the square root sign is covering everything. But basically, you'll just put that in and get a number. I think, yeah. Yeah. There it is. All right, and that's basically it. You got to just add up 3 pieces. Very conveniently, the 5 over 2 pi's cancel. That's nice. That's a good thing to point out, I guess. Don't calculate, don't put those in your calculator, the 5/2 pi, okay? Because you're going to, if you do that, then you're going to have this decimal that you're going to have to write out. You're going to have to round it off and all these things. When at the end of the day, those two just canceled each other out. So you never had to calculate anything there. And this happens a lot. So try to hold off on using the calculator until the very end. All right. And then final answer. 24.1 approximately, not exactly, but there you have it, to 3 significant figures. Okay, that's number 8. Okay, number 9, part A. This is basically just a travel graph, and you need to get the idea of drawing that. That's going to be critical to answering the question, I think. So we've got speed on the y-axis and time on the x-axis, and we have, I'll draw it in a minute. Basically, we have two sections of constant velocity, so those will be horizontal lines, and then we have a middle section where it's constant deceleration, which is also a straight line. Okay, so all the lines are straight here. That means there's no need for calculus. So as long as you draw the travel graph and you'll set the distance 458 meters to the area and you solve for W. So we'll see that one is fine. Part B, we have a different velocity function. It's a quadratic there, you see. It's in factorized form, t minus 4 times t minus 5. Okay, now we will use calculus here because this is a curve. It's not a straight line. So to get the area, we'll need to use calculus. All right, so let's get into A. So we're going to draw the graph. Velocity on the y-axis, t on the x-axis. Okay, so we have these two velocities that are given to us. Not really given, they're unknowns, but we're going to solve for them. Okay, so we got the first velocity, which is w, and then we got the second one, which is w minus 14. And then what you want to do now is mark down these critical points. We start at time 0, and then we have 12 seconds, 10 seconds later, 22, and then 50 at the end. And we're just going to connect the dots. And there you have your travel graph. All right. So what is it saying? It's a translation of the words into a graph. So you've probably done this. The first section, the first 12 seconds, constant velocity. That's a horizontal line. Then we have a constant deceleration for 10 seconds, which brings us to 22 seconds. And it slows down to w minus 14 and then maintains that velocity for 28 seconds until t equals 50. All right, so to find the distance, all we need to do is get the area under the graph. To do that, I'm going to cut it into 3 pieces. First piece is a rectangle. Okay, this one's pretty easy to get. I know the width is 12. Okay, that's on the x-axis. And the height is w. That's one piece. Second piece is a trapezoid. Okay, so it's a trapezoid on its side, right? So we will take the base, which is 12 to 20, 12 to 22. Okay, the base is 10. And then we basically take the average of the two sides. So the left side is w high, and then the right side is w minus 14. So those are in the numerator. We divide by 2. This is just the area of a trapezoid. All right. And then there you have it. Then we have a rectangle, and the width of the rectangle is from 22 to 50, so 28, and the height is w minus 14. We just read that from the y-axis. All right, that's it. We know the total of that is 458. And so now all we need to do is simplify all this stuff. Okay. Multiply out those brackets. This is no problem, guys. A nice one. Combine your like terms here. Yes, indeed. Almost there. Going to divide by 50 now. And we get W is equal to 18.4. Okay, part A. As long as you thought about drawing the travel graph, you're fine. Okay, part B now. I realized actually that I did B2 first. So here's B2. B2 is just, again, drawing a graph is very helpful. This is an easy one to draw because we know it's a quadratic and we know the roots, okay, because it's given in factorized form. So the roots are 4 and 5. So we can draw it just like that. We know it's pointing up because it's a positive x squared. And so B2, the section where the velocity is negative is 4 to 5. Okay. It's 4 to 5. It's not equal. So just t greater than 4 and less than 5. Okay, now we're told, let's see, we want to find out where the acceleration is 0. And the acceleration is just the derivative of the velocity. So we just want to find out where the derivative is 0. It's the minimum point, by the way. You can do it without the derivative also. Let's do it with the derivative. The derivative is easy to get. Okay, notice I didn't explain this, but I expanded the brackets first before I did the derivative. I think it's easier. You could use the product rule on the two factors. Either way. We set it to 0. Yeah, simple one to solve. Add 9. Divide by 2. T is 4.5. Okay. Now you could have done it without the derivative if you recognize that by symmetry, okay, you have that line of symmetry. It's going to pass through the minimum point, which is where the acceleration is 0. So that's halfway between 4 and 5. Okay. All right. Now we need to find the total distance traveled from 0 to 5. Okay. And so this quadratic, now I can't see the y-intercept. It's way up high there, and so it's not on the graph, but it touches there somewhere. So basically we need the area under the curve from 0 to 4, okay, because the distance is the area under the curve. And then we need to, the section from 4 to 5 will give us a negative area because it's under the x-axis, okay, negative distance. But we want to know the total distance traveled, and so we want that negative part to add to our total distance. So we have to subtract that. So we'll be subtracting a negative area, which we'll be adding on to the total distance. Okay. if you can't get your head around that right away, just pause and think about it. But I'm subtracting it because I'm subtracting the red piece because it's a negative, and I want it to contribute to the total. So if I subtract a negative, it'll add to it. All right. So now all we need to do is get the integral here, split it into the two pieces as we said. Okay, we're just using the power rule, so no big issues with the integration. And we just have to evaluate it. Okay, in the first one, we put 4 in. That's what we get. 0 is nothing because there's t's all there. The second piece we evaluate at 5. And then at 4, which we've already done, so we can just repeat that. Okay. So now just be careful of the brackets and the minus signs. Make sure that you've got it all together like this. Okay. You'll notice now that we have 2 of those things because in the second integral, it's a minus and negative. So 2 of those. So it's just simplifying here. Going to multiply the 2 through the bracket there. All right. And then I'm going to combine all the whole numbers. I don't know. There's different ways you could do this. Just take all the whole numbers there, and I've got fractions remaining. Okay. And then we see that we have to make a common denominator. So it's going to put everything over 6, even the whole number. Okay. So everything over 6. And then we just add it all up. Get that? That's the distance. Can we simplify? Yes, we can. Divide by 3. And there you have it. Total distance, 59 over 2. Okay. Key here is to know that you need to split up the integral into those 2 pieces because you have a positive and a negative piece. All right. So that's all. Critical here for both of these to draw the graph, I think. Yeah. All right. Number 10, we have a vector question. So we've got 2 position vectors, P and Q. Position vectors start at the origin, and then P goes 3 to the right and 2 down, and Q goes 8 to the right and 13 up. All right. Then we have point R, which is on PQ, and PQ is 5 times as big as PR. Okay, we'll have to draw that to get a good sense of what's going on there, I think. Part B, we have another position vector S. So starting at the origin, and it's given as a lambda. So lambda some number times j. So you notice there's no I component, which means it doesn't go left or right. That means it's if you think of the number plane, it's on the y-axis. Or another way to think of it, it's a vertical line, vertical vector. All right, and also it's parallel to PQ. So we'll have to look at PQ and then see what this all means. Okay, so you need to draw these things. Does not have to be perfect or to scale, really, but you need to have the vectors to be able to see what to do here, I think. I don't imagine you could do it without that. Okay, so here's my drawing. We have O as the origin, vector OP in blue, vector OQ in green, and I'm going to draw PQ because that's going to be needed. Then we have this point R, on PQ. OR is the position vector. And we know that PR is 1/5 of PQ. Okay. So how we want to find OR and how do we get from O to R? That's how we answer these vector questions. So how do we get from O to R using what we know? We can go down, we can go from O to P because we know that, and then we go from P to R. Okay, so that's the path in yellow. So it's those two vectors. Here are the numbers for the vectors in matrix form, just a different way of writing it. Again, OP is to the right 3, down 2. OQ is to the right 8, up 13. Okay, so you should draw your vectors like that. This illustrates how you get from O to R. All right, and then we have to do the working out. Okay. So we know OP, that's fine. PR, we know is 1/5 of PQ. Now we need to find PQ. All right. So how do we get from P to Q? We can go from P to O. All right. That's the opposite of OP. Opposite just means negative. Okay, so negative OP plus OQ. That's how we get from P to Q. All right, so we put that in. Negative OP plus OQ. And we know those things. So we just have to put the numbers in now. There's OP. Negative. Actually, I put the OQ first, and then I'm subtracting the OP. Just switch the order there. Okay. All right. So the bracket on the right there, we can combine the I's and the J's. We get 5I, 15J, nicely divisible by 5. So we'll multiply that 1/5 through. Okay. Finally, combine those I's and J's. You get 4I plus J, 1J. Okay. Almost done, not quite. We still need to give it as a unit vector. Unit vector means it has magnitude of 1. So the way we can get a unit vector is get the magnitude of OR, and we divide by that magnitude. That will make the magnitude equal to 1. So here's how we find the magnitude. Square root of 17. And there you have it. I notice I put 1J there. That 1 is unnecessary. But it's also not wrong. Okay, so that's the unit vector in the direction of OR. Fine. All right. Now, I want to show another way of doing this without using vectors, actually. You can just put these 2 points from the position vectors. Okay, point P and point Q. That's the blue and the green. Okay, now R can be found by using a weighted average. Okay, so if we think about, let's stop it here. Okay, that 0.5 is indicating the proportion out of 1 from 3, -2. Okay, so here's the midpoint, right? How do we get the midpoint when we have those two endpoints? We just take the average of the x So 8 plus 3 divided by 2, that's 11 over 2. And we take the average of the y's, 13 minus 2. So that's where we get the midpoint. Okay, so you can think of the midpoint as a weighted average. It's 50% P, 50% Q. Okay, now as this moves around, okay, the proportion changes. There, if I stop there, we're 100% 8 and 13, 100%, because it's all the way. The proportion of it of S is obviously it's sitting on top of Q, all right? And so that number in white just shows the proportion, right? This would be 0% green, so that means 100% blue. All right. Now I'm going to move it to where we are, which is 0.2. Okay, it's 1/5 of the way to green. And so we need a weighted average. Okay. And so it would be basically 4/5 of P and 1/5 of Q. Okay, so if this makes sense to you, you can do it this way and avoid the whole vector thing. Just simplifying now. And it works out nicely. And you see you get the same. What do we expect? 4, 1 for R. Okay, then you still would have to get you have to divide by the magnitude for the final answer, but that's how you get the point R. All right. So that's the second way of doing A. Let's look at B now. So B is this vector OS somewhere on the y-axis. All right. So we also know that it's parallel to PQ. So I'm going to draw this line here that goes through P and Q, right? So what we need to do is find, let's see, the point S that is on the y-axis and also on that line. Okay, so that's just the y-intercept of this line in pink. Okay, so we can don't really need vector things here. It's just straight line graph information. So we're going to use the point gradient equation of a line. We have 2 points on this line, P and Q, and we just want to find the y-intercept. So I'll use the point Q. Here's the gradient, change in y over change in x. And then subtract the x value of Q. Just work this out now. Kind numbers, once again. The gradient is 3. And then we have to put it in standard form so that we can see what the y-intercept is. Okay. So there we have it. The y-intercept is -11, and that's our answer for S. It's that point there where the line crosses the y-axis. Okay, that's it for number 10, vectors. It's critical, I think, to draw the vectors. If you can do that, and then if you are faced with a question like, what is this vector, you have to think about, how do I get from this point to that point? You can go in any direction. You follow these vectors that you know about to get to where you want to go. Okay. Also, we saw a couple ways that you could avoid using vectors and just answer these using the coordinates on a number plane. All right. But it all comes from picturing what's happening here, I think. All right, on to 11. Okay, on to question 11. Talking area here with a curve, so you need to definitely make that connection that we're going to do integration here. And then we just need a strategy on how to find the shaded region. So let's see what we've got. The curve is given there, 6 plus e to the 4x minus 5. And then it's bounded by that line segment AB and x equals 2. All right. So find the area of the shaded region. Okay. So with integration, we know how to get the area under a curve. So basically, the strategy here is to take, you have a rectangle, right? And you subtract out the area under the curve, and that will leave the shaded region. All right. And so let's see. One thing to think about is so we know the length of the rectangle, it's 2, right? From 0 to 2. And so we're going to need to get the height of the rectangle, and then we just do the integration. So this actually, for 7 marks, if you know what they're getting at, the work's not too bad. Not too bad at all. All right, so let's see what we have here. I'm going to just show in shapes what we're doing. Okay. So without math symbols or words, I think this is kind of neat. What we're doing is we're taking the rectangle and we're subtracting the area under the curve. That gives us the shaded region, which is what we want. Okay. Now we need to convert that into math symbols. All right, so let's see. First of all, okay, there's the function. And basically, I need to get the value of the function there. Okay, and that's when x is 2. So really not a big deal. All we do is we put in 2 for x, and we get that. Okay, now don't put that in your calculator. Just leave it as it is. Okay, otherwise if you put it in your calculator, you have to round off, and you got to write a bunch of digits, and just leave it there. We'll see what happens. Maybe it'll even cancel at the end. So that's the height of the rectangle. All right. And it's also the equation of the line, so I'll put it there. All right. So how do we express the area of the rectangle? So it's the length times the height, so it's 2 times that. And we'll just simplify a bit. Okay, how do we get the area under the curve? That's where our integration comes in. So the limits are from 0 to 2, and you just put the function in. So let's go ahead and calculate that. Okay, so the actual integration, really not a big deal. I'm not going to go into that too deeply. Hopefully you're good with that. And then we're just going to calculate it at the limits. So we put in 2. Boom. We'll put in 0. All right. So we're just going to get a value here. I'm just simplifying. Yes, it's about as far as we can go now. All right. So now, pretty simple to get our shaded region. We just get the difference of these two. And yeah, that's it. Our 12s cancel. That's nice. We have e to the power 3s that we can combine. So we got positive 2 and a negative 1 over 4. That gives us 7 over 4 e to the power 3. Yeah. All right, and then you can put it in your calculator at this point, and we get 35.2 to 3 significant figures. 7 marks. I really think that one is doable. It's a quick one. Of course, it depends on you knowing what we use integration for and having a little practice in that. But I think like this one is where you can really get a good chunk of marks for a short time. All right, and we're almost done. One more to go. All right, so finally, question 12. We're going to get into 3D shape. Okay, so we have a pyramid, and the base is an equilateral triangle. Inside the pyramid, we have a triangular prism. Okay, the top and the bottom of the prism is also an equilateral triangle. And what we're going to do here is we're going to be changing the height until we can find the maximum volume of the prism inside the pyramid. Okay. Now, another shape that we have that we're going to have to think about here is a smaller pyramid, which is formed by the top of the prism, right? So as the height of the prism goes up, that smaller pyramid, the pyramid getting smaller. So you got to think of having here two different pyramids. Okay. Because we're going to need that for a similarity argument. Okay, so anyway, part A is going to lead you into getting an expression for V in terms of H. Okay, and that will be needed for part B, where we will take the derivative of that to find the maximum value of the volume. Okay, whenever you see maximum value of something, you should immediately think of the derivative. All right, so let's take a look at this shape. So we have a pyramid in orange. We have a prism in green. So let's look at what happens as we change the height. Notice the volume of the prism. That's what we're interested in, how that changes. Also notice, try to see the two different pyramids. You have the original pyramid, okay, in orange, and then you have a smaller pyramid that changes as the prism changes. Okay, so let's just get our vantage point so it really does look 3D. Yeah. All right. Okay. So let's move the height, change that around a bit, and notice the smaller pyramid. That's important. Smaller pyramid. Okay, volume changing. Okay, when the height of the prism is equal to the pyramid, it has no volume. All right. So that's what happens to the prism. And just notice that you have that smaller pyramid that also changes. Okay. So you got to also note the given information. The height of the pyramid is 12. The length of the side of the base of the pyramid is 8. All right. So that is what it looks like in 3D. But really, what you normally want to do here is boil it down to a 2D problem so that we can do normal calculations that we're familiar with trigonometry and whatever similarity we're going to use here. Okay, so we start looking at the base of the pyramid. Base of the pyramid is an equilateral triangle with side 8. Okay, that's nice. Here is the base and the top, so the top and the bottom, same shape, right, of the triangular prism. And we don't know the side of that because it depends on h, right? S depends on h. And basically what we're going to do is get S in terms of h. All right. So to analyze this triangle, let's draw the height of it. That cuts it into two triangles, and each one of those two is a 30, 60, 90, which is so famous. It's a famous, famous triangle that you really should know it. If you don't get to know it, I would suggest. Because it's a 30, 60, 90 triangle, we know the height in terms of S. Okay. So let's tuck that over there and do our algebra. Okay. So now we have this similarity relationship. Okay. So on the left side, I have in the numerator the height of the small pyramid. Okay. And that changes with h. So as h goes up, that small pyramid gets smaller. So remember, h is the height of the prism. Okay. And then the original pyramid is 12. Okay. Because of similarity now, S is the side of the small pyramid. So that also changes with h. And it's by similarity, right? The proportion of the height, let's say the small height to the big height is equal to the small side to the big side. Yeah, so that's similarity. All right, so there's the small pyramid height, big pyramid height, small pyramid side, big pyramid side. Okay, so now we can get S in terms of H because you don't want two unknowns. We just rearrange this, simplify. There's S. Okay, so we'll tuck that over there. We're going to use that. Okay, so we only have one variable now, and that's H. Okay, so the volume of the prism is equal to the area of the base, so that's the green triangle, times the height. So that's the green triangle that we're looking at. That's the base. Okay. And how do we proceed? So the area of the base is just area of the triangle. So we have everything we need in terms of S. Okay, and then we have H. So we're going to just write that out. Yeah, that's the green triangle. All right, and then let's put in, rearranging here a little bit. Yeah, okay. Exactly. We got S squared. Okay. That just makes our substitution a little cleaner. Now we put in S and we square it. And you just got to do this algebra and be careful. Expanding the brackets. Fours cancel. That's nice. All right. Well, this is just algebra. That you need to be good at. Combining. I put it in a descending order because that's more normal. And that is what we're looking for part A. Okay, so we have an expression for the volume in terms of H. That means that we can take the derivative of the volume, and it's a pretty easy derivative to take, just using the power rule, and we set it equal to 0. So this is Nothing too bad here. You can throw out the square root of 3 over 9 because we have 0 on the left side. And we also have a common factor here of 3. So I want to simplify this as much as possible. So hopefully I can factorize it. All right, can we factorize this? Yeah, you'll see. Okay, I can make 48 with 12 times 4, and I can make, well, negative 12, negative 4, and I can make a negative 16. Factorizes. This is really working out nicely. And then let's just think about our two answers. Usually there's a reason to throw one of them out. And also it's important to remember that when you set the derivative equal to 0, you could be finding minimums or maximums, right? And so let's look at the answers here. We have 4 and 12. And we can throw the 12 out, right? Because we notice that when the height of the prism is 12, its volume vanishes. It's 0. So we're left with 4. And that is it. That's what we're looking for. So when the height is 4, that is the maximum volume of the prism. And I must say, calculus is cool. It's just cool that we're able to do that. We can find the maximum volume using calculus. You think of those things changing, and how would you know exactly? Okay, you could probably devise a way of measuring, maybe filling it up with water, something like that. But calculus gives you the exact answer, just on paper. Okay, that's the end of this exam. As usual with AdMath, they really require you to be sharp with your algebra. And if you're really sharp with your algebra, then the rest of the math is more fun, I think, and interesting. You just need to be able to do that, the task of, algebra, being careful. And if you can do that, then you have a future in math, maybe. Okay, that's all for now, and maybe more to come. We'll see.